Okay. So let's return to training a deep generated models. We often want to train the models that can help us to generate novel data samples, right? And the new data should be realistic, for example. That is a training phase, and the core the core of this model often are often neural network, right? Very complex neural network. As we studied before, we already studied about VAE, right? It is a framework that can help us to train some generative models. And diffusion, it is another family. As you can remember, we use a neural network um, to learn the hidden representation for the data, right? For the image, for example, and then based on a hidden vectors, you can produce a new image based on the latent vector, right? What is the one of decoder? Okay, so in order to generate a sample like this, you just use your trained models to produce one image like this, right? This is the sampling phase, or sometimes we call that generation or inference, right? And before diffusion, there is another family of models that is very strong. It is GAE. And of course, GAE, it also made a breakthroughs in AI. And for many years, this type of models dominates generative models, generative family. Until 2020, that is about 6 years before, a very simple model, it is known as diffusion models, DDPMs appears, then a lot of models can help us to generate a very high quality image. For example, in 2021, we can train a model that can generate some very high quality image like this, for example. Okay, and at that time, this kind of model already outperformed GANs. So, and 1 year later, there are some open systems that can enable any users in the world can produce a very high quality image, for example. For example, DALL-E or imaging from Google, DALL-E from OpenAI, for example. Right? And those systems often based on diffusion models. Okay, so let's study what is a diffusion model. We first study about some ideas from a very well-known models. It is the noise and diffusion probabilistic models, and this kind of models already make breakthroughs in this area. Okay, for these models, it has two components or two processes. The first process, it is known as forward diffusion. It essentially adds noise gradually to a given image until we obtain a completely noise image, right? So in that case, the image is already a noise. We cannot recognize anything about that image. Okay, for example, when we can, this is the original image, then we add one noise, we can obtain this one, and we do the same for many steps. until we can obtain something like this without any meaning for human, right? That is a forward process. And for this kind of model, this process is often fixed. That is, we fix one way to do noisy, to make to transform one image to a noise, right? Okay, so this is not learned. Another process is forward, a revert process. Or in other words, we can call that denoising process, right? We can start from one noise vector like this. Then we try to remove the noise gradually until we can obtain a very high quality image like this. Right? Those are two main processes in this kind of models. Very simple idea, right? And of course, this step or this process should be learned, right? After learning, we can use this model to generate new samples, right? Just based on from some noise there, we can produce some new samples, right? And once we have that models, we call that generators. Okay, so for the forward process, we can fix the number of steps in order to transform from the original image to a noise. For example, we choose T, big T, for example. Okay, we start from X0. X0 denotes the clean image, the original image, dated, real dated, okay? Then we add one noise to obtain X1. Then we add noise more to obtain X2, etc. We can do many steps until we obtain XT, okay? And XT here can be considered to be a noise when T is large enough. For example, 1,000 steps. Okay, and the way we add noise is very simple. We just model this process as a probability, right? Means that XT in the next step should follow a distribution. It is the normal distribution with mean based on the previous image, the given image, right? So after many steps, in fact, we are working with some distribution for those noisy image, right? For example, we denote by X1, X2, XT. Those are to be the noisy image. Okay. So in fact, we are trying to work with the distribution, the joint distribution of all of those vectors, those images, right? And because the generation of one image is conditioned on the previous one, right? So this process is conditional or sequential, right? So it means that the X in the next step depends on the image from the previous step. And we can write, and we can assume XT to follow some distribution Q conditional on XT minus 1, for example, right? And by this way, sometimes we can call that the forward process. It is, in fact, follow a Markov chain, right? We move from one step to another step. And of course, for diffusion models, this step is often fixed. We choose one way. We can fix one way to produce the noise image. For example, we can assume that each by this way we choose a Gaussian distribution, right? Means that the next For the next step, each image follow a Gaussian distribution with the mean, but this is to be the mean, right? And the mean here depends on the previous, the image in the previous step. Okay. Okay. In other words, we can write that distribution to depends on the real data, because we can write after many steps, xt depends on xt minus 1, and also depends on xt minus 2, etc., right? And then after some writing, we can even write xt can depend on xt 0, depends on real data, right? So that's why we can write the distribution to be like this. The distribution of xt condition on x0. But it's also normal distribution. Very interesting, right? This is a very nice property. Even though we do many steps like this, but overall, any xt here is a Gaussian variable, normal variable. Sorry, no, Gaussian distributed variable, right? And for that distribution, we can compute the mean to be like this, and this is the variance of the distribution. That's very nice properties. We can write in an explicit form, right? Where alpha t bar is computed by this formula, and beta s here represent the scalar. Okay, those are some constant, and we can choose those constants so that this process can help us to move from real data to some noise after this step. And each distribution here, sometimes we call that the diffusion code. Okay, the reason we can write the conditional distribution like this can be explained in this figure. For example, from xt, it depends on xt minus 1, right? Because it follows the Gaussian distribution with the mean here and the variance like this, right? And you can remember one property from the Gaussian distribution is we can represent any x to be the sum of the mean with the variance with a standard noise, for example. That's very nice property from Gaussian normal distribution. Okay, and then from this one, we can write it in terms of xt minus 2, for example. And then after many steps, you can write that some equation that depends on x0, depends on real data, right? And this is what represent Gaussian distribution. Okay, so that's why we can write something like this. Very nice property, nice property. Okay, so by this way, as we explained before, this distribution means the xt can be represented by this sum, where the first term represents the mean, right? And the second term contains the standard deviation from the distribution and one white noise, right? This is a very nice property from normal distribution. And for diffusions, in order to assure that we can move from the real distribution to the noise distribution, we need to choose some constant so that this should converge to some noises. Or in other words, we try to choose beta so that this constant should go to 0. Okay. So when this goes to zero, that means that xt big T here, right? It is just a white noise, right? And when we choose this one, we call that a scalar. The noise is scalar. Okay. Any question? Okay. One question. Let's compare with VAE. In VAE, we also have two different steps, right? One is encoding, the other is decoding. How about this? Is this similar with encoding or decoding? This process, the forward process.
Encoding
Decoding? Can you say it again?
is the same with encoding.
Encoding. Okay, it's right. So for the if we have x0, then we can put it through one encoder to obtain a latent variable, right? A latent representation. And then from this, this is one phase. Another phase, in order to generate one image, we can put a latent vector to the decoder. And then you can say something. Another thing, we use decoder to generate images. Right. Okay. So for this step, we are working with some distribution. For example, we have the distribution of the real data, right? And then we work with the distribution of latent variable, conditional real sound. And then you got the encoder compare to map from this one, right? Here's that one here and map to how much you. So what is the role of the encoder? It is a mapping from one example to a distribution. And of course, for VAE, we need to train this encoder, right? So compare with diffusion, we move from a real example to another thing, right? For diffusion, we do not train anything here. We just fix, right? Fix the process. So we do not have any. How about you? You know, in general, what we use, right? So, for military input, it can map from one D to where? Okay. How are you? Do I do? Really? Yeah. That's the condition. Condition on. So in my community, what? So distribution. You are conditioned. Yes, I got it. Okay, it's still visual on C. I'm sure. You agree with me? So let me for example, when you use again, it is a map. You can map from one input to another output, right? Okay. So when we say about this, what is that? So the output is the how we can represent that. Let's act zero. Yes, this is correct. It's not from one level to a condition. And then the other thing is a new network is represent one equal. And it's used to here, it is about it. And then the output is impact the mean, right? For example, the mean, we can read it as the mean. And third, it is a function of mean. And the mean variable, mean represent what is one value. Another thing we can use a decoder to generate any sample. So for the we need to create both, right? Create both decoder and compare it to diffusions. We fix one step. It is a forward step, right? Forward process. We just fix one way to generate. No learning here. We just learn and generate it. That can help us to do the reverse process, right? And then it can help us to generate some image in the future. That is very similar with decoder, right? Sometimes we call we can call the model that have to do the reverse process. It is the noiser sometimes. Okay. So let's see what we are doing with the forward process. We start from a real distribution, right? At each step, we will try to make noise to the sample, and we make noise many steps. How about one step? Okay, for one step, for example, we start from this one. It is a data distribution, right? And the data distribution sometimes can be very complex, right? Then, if we add noise to the sample here, it means that we move to another distribution. We did it by Qx1. How to represent Qx1? Okay, let's rewrite Qx1. It is similar with this one. For example, let's consider here T to be 1. Okay, so Qx1 can be represented by the integral of the Qx0, x1. This is the joint distribution, right? And then if we take integration over x0, then we will obtain Qx1. That is a very basic property from probability, right? Okay, now let's decompose this joint distribution into the product of Qx1, x0, and Qx1 given x0, right? So we can see that this is a data distribution, and this is the diffusion kernel, right? The kernel we already know here, for example, this is the diffusion kernel. We already have a form, right? Or in other words, by this way, what it means, we are trying to smooth the data distribution in order to obtain Qx1, right? You see this? We are trying to make the data distribution to be smoother. Okay. It is the expectation. Can you revise this? Can you revise this? From this one. Because by definition, right? The definition of expectation, according to your distribution, right? There, it is in fact really. Okay, so now, this is the expectation or average. So what it means? Can we write by the same way? For example, we can decomposed by one, that is 0 x1, right? Now we can control that. B x1, B 0, B x1, B 1. Okay, so by this one, it is the expectation over x1 plus B x2. Sorry, it is not like this will be you at this. And we can remember that x1 can be represented by a formula similarly with this, right? Very similar. So what it means, we are working with it. You know this. This is the x1 here. Here, oh, x0. So by that way, you can see that the distribution qx1, it is the result of a convolution of a convolutions between the diffusion kernels and the data distribution, right? When we write something like this, okay? So when we work with convolutions, remember that it is a very well-known operations to um, some function, right? And when we use convolution, we can interpret that it is one way to smooth the original function, right? And when we apply here, we are trying to make convolution for the data distribution. So it means that this distribution should be smoother than the original distribution, right? And next, if we add noise more, we will obtain QX2, okay? And this distribution should be smoother than the previous one, etc., right? And after many steps, you can obtain a very simple distribution like this. It is a white noise, the standard distribution, right? So what is the meaning of the forward process? Okay. We're trying to transform a very complex distribution to a very simple distribution, right? And of course, from this simple distribution, if we know how to reverse, how to denoise, then we can generate a new sample just based on some noise. For example, for each step, if we want to generate one sample based on um, the data, then we first sample 1 point from the data distribution, and then we can sample xt according to the forward process, right? So the forward process is very simple. We can choose. The remaining part is to learn how to do the reverse process, right? That is how to generate one image. Okay. So essentially, in order to generate one image, we can start from one noise, right? For example, you can generate one noise here, and then you try to denoise that, right, to obtain another point, and then denoise that to obtain another point, right? And after many steps, you can obtain one point that can follow the data distribution. That is the denoising process or reverse process. Right? And of course, when we do something like this, it is in fact, we are trying to do some sampling, to do many steps, to do many sampling process, many steps, right? For example, in the first step, we just do sampling from the white noise, right? The standard normal distribution. And then for every other step, we just take a sampling from the conditional distribution, right? Okay. That is the idea of to do reverse. But in practice, this distribution is unknown. We know the distribution of xt given xt minus 1. We already choose to be a Gaussian, right? But the reverse is not Gaussian anymore. Okay, so that's why this distribution can be very complex. So the question is how to learn this distribution. But it talks of learning, right? Okay. So let's focus on this step. We want to do sampling, right? We assume we denote by p xt to be the white noise, to be the standard normal distribution, right? With mean 0 and unit variant. Then we will train a models that can help us to learn the distribution, the conditional distribution of xt minus 1 given xt. Okay? And we are trying to learn this distribution in the form of a Gaussian distribution. And it means that this one should have a mean, we denote by mu 0, right? And a variance to be sigma t, for example. Okay, so sigma t here, we can fix and we can choose to be similar with the forward process, okay? And we just focus on the mean, okay? Because the mean here, if we know that, we can write xt minus 1 based on the mean. That is very, very, very efficient, right? Very, very good. Because this is the Gauss. Okay. So in order to learn the mean, we can use a neural network, right? With the input is xt, and the output should be the mean. That is very, very similar with the decoder here. Very similar. Okay, so by this way, we in fact are trying to learn the joint distribution of x0, x1, etc. to xt, right? And of course, that joint distribution can be represented by this formula, right? Just use as a chain rule. Okay. So here we work with another distribution. This comes from the model, right? The model we work with, but the true distribution is different, right? What is the true distribution here? This is a true distribution, and this true distribution is very complex in reality, right? So we cannot work with this directly, but fortunately, we can write this distribution very easily. And this one, this is the distribution of xt minus 1 conditional on xt and x0. This one, we can write this distribution to be explicit because it has a normal form. That's very, very lucky, okay? So the idea to train the model is we will use a neural network that represents this distribution, and then we try to match this one to this one, okay? Instead of the original one, right? That is the main idea. That means that when we focus on the second quantity, one way to train the model is to minimize the distance between these two distributions, right? The KL diversion, for example. We can minimize this one. Okay. Do you have any question?
No.
Okay. So if you want to understand why this conditional distribution can be a normal distribution, you can see the detail in this slide. After some derivation, you can write explicitly what is the mean and what is the variance based on the base rule. Okay, and the mean here, it has one explicit form. For example, this form is like this, and the variance also have a very explicit form. Okay, so it means that this distribution is tractable. We can use that. We can use that to have a trend, right? Okay. Okay, so let's return to training. Once we know that that conditional distribution is Gaussian, then our model also induce a Gaussian distribution. So based on that, we can match the distance between those two distributions, right? For example, we can minimize the distance. That's one way. Another way is we can focus on the likelihood of the data sample, right? We can borrow some idea from VAE before. In order to train VAE, we can start from the likelihood, right? And then we maximize its lower bound in order to train the models. That is the idea of VAE. For diffusion, we can also do something like this, okay? Here, for example, let's consider the negative log likelihood of x0, okay? This is a negative log likelihood. And this quantity is, if we add one constant here, so this quantity should be bounded by this sum, right? Because the distance here is at least non-negative, right? So this is the upper bound for this quantity. Okay, from this KL version, we can write it in details, and then after some writing, some reformulation, we can obtain a new quantity to be like this. It is expectation of according to Q of this ratio. Okay, very simple. And this one, we can consider that to be the upper bound of the negative log likelihood, right? And we can use this to have a trend. For example, we can consider this to be the loss, right? To be the loss. And then we can minimize the loss if we want to trade. Right? Okay, so we denote L to be the expectation according to the joint distribution from x0 to xt of this ratio, okay? And you know that this is an upper bound of this quantity. Okay, and after many expressions, you can write that function to be the sum of many KL diversions. Okay, that is very lucky, right? And the KL diversion here measures the distance between the two distributions in the same step from the forward and the backward step, for example. Okay, so in detail, the L function, it is the sum of many L, okay? And each L, it is the KL diversion between two distributions, okay? And those distributions, they are very good because they have a specific form. They are Gaussians, right? So for Gaussians, we can measure the KL diversion very easily. It has one explicit form. That's very lucky. So we can write each component is a loss to be the KL diversion, right? And in fact, it has this form, hierarchy, right? The diversion between the two Gaussians, we can write it very simple, right? Like this one, where mu t here, the first mu t come from this conditional, this conditional distribution, right? And mu zero come from our model. So by this way, you can see that This is the distance, the square distance between the two mean of those distributions, right? And each mean here, we can write in a more explicit way. For example, the first mean can be expressed by this formula in terms of a noise and XT, right? And the mean from the model, from our models can also be expressed by this way, where epsilon here, epsilon zeta, represent the network we are trying to use. Okay. So up to now, we already know the objective that can help us to train the model, right? One way to train the model is we can train the model to learn the mean of the conditional distribution. And that conditional distribution can help us to do sampling, right? To do the reverse process. We can learn this one, right? But another way is based on this expression, we can use a new network to learn the noise. Those are two different ways. And in practice, some authors find that if we learn the noise, the quality of the models can be very good compared with learning the mean of the Gaussians. That's very interesting. Right? How about in your opinions? Why learning the noise can be better than learning the mean of the distribution? Any idea? That is very interesting observation, but it is still unclear why the learning the noise can be easier than learning the mean. It's still unclear. But in practice, when we learn the noise, the trained model can be better. That is, the image, the generated image can have better quality. Okay, so um, when we work with that objective, it is a sum of this this term, right? And each term here represents one step. It is the expectation over all the samples of the data distribution and the noise from the standard normal, right? But in this objective, there's some constant here. This constant. If we choose some beta t, so that the forward process should go to the white noise, right? So this should be decreasing. Sorry, should be increasing. Okay. So beta t should be increasing when t increase, for example. So by that way, this constant can be large for small t. For example, when t is 1, 2, for example, this quantity can be large. So it means that in the objective function, some of the first term can dominate the other terms in a training objective, right? And it means that the training phase should focus mostly on some of those steps, but ignore many other steps. And as a consequence, the trained models can be not good. And this is observed in practice. So the author of these models proposed to remove that constant. And they just focus on a very simple objective here to train the models. And this is the final objective for training. Okay. Okay. In summary, in the training process, even though the deliberation of the model is quite complex and the learning objective is also complex, right? But when training, we just take some part of the objective at every step, right? So that's why the training algorithm is very simple. It is how we train the model. Okay, we do many steps until conversion, and at each step, we first take one real sample, and then we pick one step index, right? And then we generate one noise vector, and then we compute the gradient of this quantity. And then we update the model parameters based on this gradient. That's all. Very simple, right? And after training, we can use that models to do sampling. And the way we do sampling is very simple. We can do T-step. Initially, we generate one noise, right? And then we try to denoise by doing two steps. First, we generate a white noise Z, and then we compute X T minus 1 based on Z and the previous image and the model, okay? And we do that for T step. Then we can obtain one image. That's all, okay? So from this, you can see that the training phase and the inference phase is very simple, right? And of course, you can write by yourself, okay? But in practice, the performance of this model is very, very excellent. So that's why it made a breakthrough in these areas, okay? Do you have any question? So for these models, compare with VAE, when we do sampling, it can take more time, right? For example, for VAE, we just take the noises, alert the pictures, and then put it through the decoder, and then we can obtain one image. So we could just use the neural network one time. But here, we use many times. And in practice, the number T here can be very big. For example, more than 1,000 steps in order to get a high quality image. So that's why this kind of model is very slow when we do inference compared with VAE, right? VAE, we just do one time, but here, 1,000 times, okay? Okay, so those are some general ideas about how we can formulate learnings and how we can implement in practice. However, in practice, some other details we should care about in order to get a good model. For example, originally, diffusion model use a special type of network. It is known as UNet. This kind of network comes from computer vision. Anyone know that? Okay. So for this, for this architectures, it uses a ResNet block and self-attention layers like this. For example, it receives one XT here with a big size, and then in the next layer should be smaller size, and then smaller and smaller. And until some level, the model trying to upsample the size. For example, increase the size until the end. The ending size should be similar with the size of the image. So you can see that it is similar with you like this, right? And of course, we have some skip connection in this model and has some self-attention layers. And another thing is, for these models, it receives another input information that represent the time step, right? In diffusion, we have many steps from 0 to t, right? Okay, so one input is to represent the time. And one way to represent is we use positive invariant or Fourier features, for example. In practice, we find that this kind of features can be very helpful to train the models. And sometimes they also use normalization layers that can help improve models. Okay? Another things in practice we should care about is the noise schedule. That is, we should choose some constant, for example, beta t, right? Because beta t can help us to move from x0 to xt, right? And we should ensure that when we go from x0 to xt, for example, the last one should be very close to the white noise. So beta here should be chosen carefully. And in practice, we often use some type of schedule. It is known as a linear schedule. Okay, but for variance, we can fix. We can fix the variance. For example, we can fix the variance to be beta t for simplicity. But you see, in the original versions of diffusion model, DDPM, and some work later is trying to work with learning the variance or improve these models by some other heuristic. Okay? Okay. So let's return to comparison with VAE. As we discussed before, it has some diffusion here has some similar property with VAE, right? It also have two parts. One part is to move from a real data sample to a noise, right? Or to a latent representation, right? That is very similar with encoding in VAE. But for diffusion, we do many steps, right? In the forward process, we produce many latent image, many latent vectors, right? But for VAE, we only have one. Okay, so in other words, we can consider diffusion to be a special form of hierarchical VAE. That is, we stack many VAEs one by one, for example. So we can use a hierarchy of VAEs, right? And and by that way, it is very similar with DDPM we discussed before. And of course, the inquiry here is fixed, right? And the latent vectors has the same dimension with the data, right? The true data, right? That is the difference, okay? And the noisy models, it is very similar with decoder. But for diffusion, we only have one denoiser, right? One model share across many steps. But when we work with hierarchical VAE, for example, like this, each step can use a different models. So we may not share anything, right? Between steps for this kind of models. So this is some connection to VAE, okay? And you can see that the training of VAE is can be can be can be unstable compared to diffusion. Do you know why? For diffusion, when we train the models, the training loss can be very stable. That is easy to train. But for VAE, it can be harder to train, and the loss can be much more unstable. Do you know why? Do you have any idea? When we train hearing, for example, it is here, and for D, we have much smaller demand. It is in 10 dimensions, but actually can be in very high dimension. In fact, area is much smaller than that. This is the dimension of very big for data. And in fact, when we create one thing here is posterior. Wow. That is the latent representation for AI input may be very similar to each other. So to only one point. And in that way, the people cannot learn anything from the data. That is a posterior collapse in VA. But for diffusion, no. So this suggests that the training in diffusion can be much easier and stable than VA. How about your opinions? Why? Yes. Okay, so he said about one week, um, for many, the decoder needs to work transform from the latent state to the basic state. Transform the very simple to very complex. So that and the very complex. The true complex is transformation. For easy to act can be very. So the decoder is to be very, very strong in order to appreciate. Really, working. So, the area of the gap between from the model to the very line of the path. That's all. But you can see that learning to correct, learning from perfect from the reader, but now for the that's why we have like that. So for the that we only have roughly 1 and the two constitute everything. So the that one there maximum two as we take the getting. So that might be how many five we can easily trade in a circle before we and most of it is a lot. But if people later and take it, straightforward. That's the one. Without anything. That's before anything. There's a constant. And sometimes it can appear for gate. Okay, so you have some, you have seen some advantage of diffusion model compared with VAE, right? But in practice, the training process for VA for diffusion is often expensive because we need to learn many steps, 1,000 steps, for example. And inference is also very slow compared with VAE, right? Those are some disadvantages, right? You can see that. Okay, you can go to this link to do some experience with one tutorial about diffusion models. So we should have some minutes break. Okay, so let's start. um, Before moving to the next part, I'd like to remind you that um, some group when we presenting the topic, their topics in from 1 week from now. I know 2 weeks from now. That is, we start presenting from 9 April. So we only have one more theory lecture in the next week, and then some group will present their topics from next week, okay, from 9 April. And for the first day, four or four or five group will present their topic. So try to present the topics in about 30 or 30 minutes, right? And then we can have some discussion. We should start from the first topic, second and third, and then some more, right? So try to prepare your slides to present, to summarize or your understanding about the topics in about 30 or 40 minutes, right? And of course, you can present also some some of your experiments with some simulation or demo when we work with some kind of models. How about online people? Are you clear about
Sorry, teacher, can you hear me?
that? Yes.
I would like to ask about as you discussed, I heard as I remember in the first lecture you mentioned about a midterm. So do we require to do one like in the few weeks later?
Yes. After presenting all the projects, then I will organize um 1 day or maybe 1 hours to for you to do a midterm. It can be a short test about the content of this course. Detail. I will provide some detail later. Okay.
Thank you, sir.
Okay. So let's return to the lectures. We already studied about some idea of the diffusion models, and of course we study about very basic model. It is a DDPM, denoising model, right? And you can see that the idea is quite simple, but its performance in practice is very excellent, right? Sometimes in practice, we may have some other needs. For example, um, the model before can help to generate some image, but the generation is quite arbitrary, right? It can generate something that is maybe far from our needs. So one thing we may work with is to provide some guiding provide some guides for the generation process in order to generate something that we want to, right? So that's why we we work with conditional generation, right? Okay. And of course, up to now, there are a lot of systems that can help us to do some conditional generation, right? We can provide some text to represent the meaning, the content of one image, and then the system can generate the image that reflect what you are trying to do. Some years ago, when we have such a system, for example, DALL-E 2 or Imagine, and those systems can generate a very high quality image based on one description, for example, based on one prompt. And up to now, there are many systems, right? Okay, so let's consider how to use this kind of system. The DPM before, it is unconditional, right? It received and no information, no guidance, just some noise, and then we do many denoising steps, and then we can obtain some image, right? Okay, so in order to control the output, there are at least 3 different ways. The first way is we can provide some explicit conditioning for the models. And another way is we can use some pre-trained models in order to provide some guidance when we do some generation. Okay, and the last way is to do without any classifying. Okay, so for the first way, the idea is also very simple. In order to generate one image based on some guidance, okay, one idea is we can encode some guide, for example, a short sentence that represent, that shows the content in one image, for example, right? We can, for example, when we train the models, the unit can receive both the image and a description about the image, for example. And then from here, we can apply DPM as usual, right? And of course, in order to integrate some guidance here with the image, we need to transform the original description into a suitable way. For example, we transform into a vector, right? Because every picture here, or the noise picture, or noisy picture, for example, they are vectors. We can represent by a vector, for example, or a tensor, right? So we need to transform the description here, into a suitable form. For example, another vector. And of course, there are many different ways, right? We use embedding of those sentences or those descriptions, right? For example, some of you will study about clip, right? It is one very well-known model that can help her to learn the embedding for text, right? So we use that models to provide some embedding, and then based on that embedding, we can integrate with the image, right? By concatenation or some other way, for example. And then those should be the input for the forward process, right? Okay, so when we use both text and image, we can train DBM as usual, right? And here's the way: the loss is similar, just change slightly. Here we have both image and guidance, right? And now the model now should receive both information, right? The latent vectors and the guidance. Okay. And in the future, if we want to generate one image, then we just put noise and guidance, right? And the guidance here come from a new prompt, a new sentence, for example. That is the idea. And of course, in order to train these models, we need some data set, big data set that contain both image and caption, right? That describes the content of the image. For example, we can use one data set like lions with 5 billion hair, for example, very huge. That's all. Very simple, right? Another way is sometimes we can work with um, some information in terms of classes. For example, we want to generate some image that belong to that contains some dogs. Sometimes we want to generate some image about cats, or sometimes about pig, for example, right? So those images may have some information in terms of the classes, for example. Okay, so in that case, we can use a classifier in order to guide the generation process, right? Okay, so in that case, you can see that when we do some inference, we need to go from noise, and then with the noise, many steps, right? And in this process, we can integrate some guidance from the classifier into this one in order to guide the generation into to some class we are trying to generate. And how to do that? Here's how. We just based on some idea from base rule. For example, assume that we have we have some we want to generate some image from the conditional distribution. We denote by P x given Y. Y here is the conditioning, right? X is the image, okay? So in order to take some sample from this distribution, we can do many steps. And for each step, we should follow the signal from the guidance, right? But what is the signal? Here is a signal, for example. We can follow the density, right? The density of this conditional distribution. And of course, we can take the gradient of this conditional density, and then we should follow this gradient, right? So what it means, when we do many steps, the next step is to follow the gradient. So it is very similar with gradient descent in optimization, right? Do you remember that? If we were trying to maximize one function, so gradient descent is, we can do many steps, right? In each step, we follow the gradient. Okay. So that's why we can borrow here, right? Okay, so using base rule, we can rewrite this conditional distribution to be like this one, right? And here we focus on xt, and we take the gradient with respect to xt. So py here should be a constant, right? So it is in fact can be expressed as this sum. The first sum, you can see that it is the probability of y given x. It can come from the classifier, right? it represents the probability that this example X can belong to class Y, right? This is exactly the gradient from the classifier if we have, right? How about the second term? This term sometimes we call that the score model, right? And of course, in these areas, there's some other family. It is a score-based model. It is very competitive with diffusion. Okay? And we are trying to work with this. So by this way, we use both information. The information from the classifier and the information from the trained model, right? This is in fact the trained model. Come from the trained model, okay? Then we can introduce some scale into that formulation. Okay, for example, if we want to focus on more on the guidance, for example, then we just put a weight here, and then we use this for inference. Okay, we just use this to follow, and then do many steps until we obtain some very good picture, for example, right? Okay, so that is the idea when we work with classifier guidance. But in practice, sometimes the classifiers can never be trained on the noisy image. You know that here for the classifier. For example, we train the classifier outside, right, before training diffusion, for example. So, and that classifier can be trained on clean data, very good data, right, very good image. But here we need to use some noisy image like this. How about the quality of this one? When the input is changing, how about the output? Do you have experience about this? After training a classifier, then you use that model to make prediction for the new input, right? But the new input now, it is noisy, sometimes very noisy. Okay, how about the quality of this model? How about the prediction? Do you have any experience about that? No? No one? In this situation, your classifier can basically one theory. It is distribution. That's a thing. A changing environment, right? And in practice, your model can be very, very bad. So in that case, the guidance signal here can be very bad, right? If you just use a fixed classifier, you train one classifier before from clean data, for example. Then you use that for guidance, and then based on this one, because XT here, sometimes very noisy, sometimes very good, right? So the input is very sometimes they're very bad. It changes a lot. And it means that the signal from the guidance from the classifier can be very bad, right? That is problematic. So in order to deal with this, one idea is when you change a classifier, you can do some trick like data augmentation. Another way is you can fine tune your classifier to noisy data, right? That is one way. For example, this is the original image, the clean image. Then you can make that to be noisy, right? At different level, and then use those to fine tune the classifier. So this is one way to make the guidance to much more better, okay? To be more robust to the noisy input. And just one trick. So by this trick, we can use a classifier to have us to generate some image with require classes, for example, right? This is just one example. For diffusion, if we use a weight to be 1, right? So this is the result. But when we increase the weight, then the output should be much more clearer to belong to some classes, right? For example, this one should be some dogs, but here sometimes dog, but sometimes not, right? For example. So when we increase the guidance signals, the weight, then we are trying to produce some image that can belong to that class, for example. Okay, but when we work with these ideas, we need to do some fine tuning, right? We need to try to do fine tuning the pre-trained classifier with noisy data, right? We need to do one more step. Okay, but sometimes if you do not have any pre-trained classifier, you need to train from scratch, right? Sometimes you need to do something like this. Okay, and then for that case, you need to assure that the trained classifier should be good, right? Otherwise, the guiding signals can be very bad. Okay. Another thing is by these ideas, we cannot use some prompt in the future, right? Because here we just use classifier. It means that you train the model to do some classification problem. But sometime in the future, we might want to generate some image with with much more complex guidance, for example. For example, some prompt. So this idea cannot be applied. So at that time, we need to apply the previous approach, right? Conditioning, explicit conditioning. Okay. Okay, any question? Yes? Mm-hmm. 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 Okay, good question. You see his question? He concerned about the difference between the two way One way is classifier guidance, and the other is explicit guidance, right? Do you know what is the difference? Anyone know? Yeah. Um, so it means for classifier guidance, we need to use the classifier at every step when we do inference, right? How about explicit conditioning? For example, here when we use y here to be class, right? Class label, okay? Yes, but by this way, it means that at every step, we also use the class information, right? Yes, and those are some small difference. What is the big difference? Mm-hmm. 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 Yes, that's right. That is one advantage, right? For explicit conditioning, we can use different type of guidance, right? Sometimes from, sometimes some other kind, for example. So the guidance here can be much more richer, right, than in the case of classifier guidance. For the latter case, we just use some very limited information from the class label. We cannot apply to prompt any other prompt, for example. So the guidance can be very limited. That's one difference. And you can see one advantage of explicit conditioning and one limitation of classifier guidance, right? How about this way? Is there any disadvantage by this way compared with classifier guidance? Yes. Mhm. Okay, so the point is it is less interpretable compared with classifier guidance, right? Mm-hmm. Do you agree with him? How are your opinions? So, do you agree with him? Okay. About interpretability, I think it is hard to say about this because we have some description here. It is much more interpretable than a class label. Like, in some sense, it is quite more meaning. Okay. Anyone? Do you see? Can you see any limitation from this approach compared with a classifier guidance? One limitation of this approach is you need to train the diffusion model from scratch, right? In order to do some guidance in infant times, the train model need to be trained before that, right? And then you can use some new prompt in order to generate some new image, okay? But for classifier guidance, no need. We can use some existing diffusion models. Then we use that to do inference. Okay. So this is just inference time. No need to retrain the diffusion model. That is one main advantage. We just use some lightweight classifier and then integrate that into the inference time, right? So it sometimes it is very interesting in some application, right? If you have some small classifier and then we use that to guide the generation process. Okay. Especially for us, we do not have a big resource to train a model like this from very huge data set, right? We can use some Christian models and then we can use that to work with our problem. And our problem may in our problem, we can train a simple classifier and then we use that. And then we use these methods to generate some image with some guidance. That is a very good advantage of this way. Okay. Okay. Any other question? Another method, it is known as a classifier-free guidance. Okay, that's it. That is, we do not use any explicit classifier as before. The previous methods require some pre-trained classifier, right? And then we use that in the way we do inference. Okay, but now we can do another thing. We can do another way without any classifier. And the idea is very simple. When we train the models, we just train that diffusion model in two different situations. One is with the guidance, and the other is without any guidance. Okay, so in this case, for example, when we use one model before, we do not have this one, right? That is the unconditional models, right? But now we extend another input. Sometimes it can receive the guidance. Sometimes we drop that, for example, right? So by this idea, in the training phase, we train simultaneously the two models. One is unconditional models and the other is conditional model. Okay, so in the future, we just use these models. So this model should unify both situations, right? So by this way, we are trying to work with two directions. One is unconditional and the other is conditional, right? And the difference from these two vectors can show some direction. If we want to go from unconditional to conditional sum, right? And we can use this as a perturbation to the inference process, and then it can help us to generate something in the future that have some guidance. Here's how. Uh, after training, we can use both, right? As the signal to do some guidance. For example, we can compute these quantities by using the model without any guidance information and plus with the direction. We are trying to do some guidance with some guiding weights, for example, gamma, right? That's all. Very simple idea. And in inference terms, we can change this one in order to do some waiting for the guidance. Right? This is some results. If we use gamma to be 1, so the information about the guidance can be very light. And this is the information about the guidance, the prompt, right? And if we increase the weights for the guidance, so these are the results for the pictures. And you can see that most pictures can represent the prompt very well, right? Okay. And in another example, when we put another prompt, if we use a light guidance, for example, the output pictures can be very diverse, but it can represent little information from the prompt. But when we use more and more weights, for example, so the result pictures can be close to the prompt. Okay. So you have another option. And of course, by this option, when you train models, you need to train two situations, right? And then you can do guidance for without any classifier. And of course, here, why here can be very complex. Not only class label, but sometimes form, right? Text, for example. Okay. So those are three different ways that can help us to do conditional generation. Do you have any question? Yes? Okay. Good question. Okay. So let's think about this. We have two ways, right? Two ways to train. One way is here. And by this way, we still need to train the diffusion model from scratch, right? And we train from both text and image. And also for explicit conditioning, we also need to train from those data. For example, we use the same data set like this, line 5 billion, for example. We use the same data set to train two different models, right? We need to train from scratch. Okay. So what is the benefit? What is the benefits of classifier free guidance? Anyone know? You know? How about online people? Do you know? Anyone? Okay, so one thing is the first methods can be um, for explicit conditionings. How about these models? The input of these models always require y, right? And that is, we need to provide some description or some form into the models, and then the model can do some generation. That is for explicit conditioning. How about in a case, sometimes we want to generate something that is independent from some prompt. Sometimes we may want to generate something like this without any prompt. For example, if we want to generate a diverse number of images, for example, if we use some prompt here, so most images should be around, should be describe the prompt, right? To contain something described in the prompt. But sometimes you want to use some generator to generate something that are very novel. So in that case, you may need to provide nothing to the conditioning, right? So in that case, the latter way, classifier-free guidance can be better. Can be better to have to fill in this need. Okay. Otherwise, for this way, if we provide something empty for the models, it may not work, right? So in some case, that way can be better than explicit conditioning. Okay, so it does answer for you. Okay, so the last part is to introduce some models that can work with text and image. That is, it can generate the image based on text or prompt. And of course, one of the most well-known model is Glyph, and then Glide, and then Dali, for example. And up to now, there are many other kind of models. For example, latent diffusion model, right? For example, and many other systems. Monitors, you can even see from the slides. Okay, it is not very hard to study about those models, and you can know some type of model that can help us to use both type of information to in order to generate something. And most systems now are often trained in terms of conditioner, right? We move from one area to some other areas. So those are very useful in different applications in practice. And the principle we already studied before, right? So, do you have any question up to now? Otherwise, we can stop here. See you next week.